this course on the fundamentals of attosecond science and technology, which we bring to you from the Indian Institute of Technology, Madras, and the sister institution at Tirupati. So, and once more, these are our primary sources of information on which we sort of found this course: the principles of optics, fundamentals of attosecond optics, femtosecond laser pulses, 3 books, and thanks to Professor Tribino for his materials and inputs. So, in this lecture, we will make, I hope, substantial progress in after recapping the couple of things that we discussed in the last couple of lectures, which are quite pertinent to even the discussion today. We will further and complete the discussion we had on the Fabry-Perot, interferometer and Etalon. We have one small piece of information and detail that is left out. I will cover and sort of finish that. After that, we will in fact, as I said in the previous lecture, make a transition more into the mainstream content of this course, which is light pulses. Okay. In this section, we will sort of gently wade into formally describing light pulses. I think we all have a notion of what it is physiologically from day to day experience and so on, but then how do I really mathematically, scientifically describe them, quantify them, and sort of evolve a framework which will assist me in understanding their generation, metrology and application to various scenarios. We will do this in the time domain. We will recap some very essential Fourier transform details, because we need a Fourier transform toolbox as we progress in this course. Okay. So, let us do that, and finally, I hope to close today's discussion with going into the frequency domain description of pulses. We may probably carry forward some of this even into the subsequent session. Okay. So, what did we talk about in the previous couple of lectures? We spoke about and discussed Fabry-Perot interferometer as a prime example and application of multiple beam interference, and as the basis for optical resonators. Okay. So, what did we this is basically an interferometer, and what did we say it was? It is basically the geometry that we considered is that of an Etalon, a polished piece of glass, an incident electromagnetic wave is shone on it, and then we essentially want to calculate, in our case, the transmittance of the incident wave from the left after passing through the Etalon coming out on the right, but it just does not come out after one pass to the right, it does multiple back and forth reflections and transmissions through. So, the beam that eventually partially gets transmitted to the right, or the beam that gets reflected to the left, either of them is essentially a sum of multiple pieces, each of which differ from the previous one by one round trip, and all of these essentially are amplitudes which we must sum over coherently in order to determine the final transmitted output of this system, either in transmission or reflection. We only worked out the transmissive part in this case, right. So, we took recourse to reflection and transmission coefficients for the electric field amplitudes R and T for the glass air interface, and R prime and T prime for the air to glass interface, and we then wrote down the sort of expressions we deduced for each piece of the beam, for the beam that went through one round trip, 2, 3 and so on and so forth, in terms of the only parameters we actually know, that is the input electric field amplitude E naught, the reflection and transmission coefficients, and the round trip phase delay, which is essentially a product of the round trip path length L, round trip optical path length L, and the wave number or the magnitude of the propagation vector k, right, straightforward. Then the transmitted intensity, we derived this, we summed up the amplitudes, we got an expression for the transmitted electric field amplitude, that is over here. But what you measure in a laboratory is something related to irradiance. Okay. So, the transmittance of the irradiance of this transmittance, which is essentially the same ratio for the irradiance transmitted by the irradiance incident on this for this problem, essentially can be written down in terms of T t prime r and delta, and we use some established expressions in order to basically write down. So, in order to write down the transmittance, we essentially we basically took the transmittance and wrote this down in terms of the capital R, which is the reflectance of either interface of this Etalon arrangement. This capital R importantly is the square of little r, which is the amplitude transmission, rather the amplitude reflection coefficient for the glass to air interface. Okay. And then a series of simplifications follow, and it leads us to defining a new quantity called F, which is only about the reflectance of the glass air interface r, that is the square of little r, and the transmittance is a neat function, which is 1 by 1 plus f sine square delta over 2. Plot the transmittance at chosen values of delta, which is essentially delta should be integer multiples of 2 pi. The transmittances peak up to unity in this case, which is a consequence of the fact that the device that we considered here is lossless, and these transmission maxima occur at specific phases. We can sweep this phase by either varying the wavelength, sweeping the wavelength, or even the thickness of your Etalon, or even the angle of incidence of the Etalon. And then there is a notion of the peaks of the transmission being sharper if the f corresponding to that particular interferometer is relatively higher than than a comparable one. So, from 200 to 1 to 0.2, of course, these depend upon the reflectances that we are concerned here with, right. This was 4 r divided by the square of 1 minus r was the definition of f, where r was the reflectance of the interface on either end. So, we also then understood that these resonances are at frequencies which correspond to these basic cavity modes. If q is the mode number, so q can take integer values 0, plus minus 1, 2, 3, 4, 5 and so on. This essentially illustrates the fact that the wave inside the resonator, the electric field amplitude which is sketched here, essentially has nodes at the boundaries and hits a maximum one or many times, as the case may be, depending on the value for the mode number, and that is pretty much like a plucked guitar string, right. So, there are special frequencies at which the transmission max is maximal, and in the comparable case where we showcased an experimental result. So, here is the frequency swept by the across the device, and here you have the intensity of the signal transmitted through. This is a real measurement. Then we looked at the shape of this transmission function, and this is something we did in yesterday's lecture, and we can look at it once more a little carefully. We wanted to quantify essentially the gap between two successive maxima in the transmission function. Okay. So, each of these peaks in the transmission function, which is now plotted against omega, which is the angular frequency. Earlier we had the cyclical frequency. Omega is written in multiples of 2 pi divided by t. What is t? Capital T is the round trip time of the wave traversing from a point in the cavity and bouncing off to reflections and coming back to the same point. So, it is the cavity round trip time. So, plot it against this. If g of omega is the function describing the shape of an individual a peak inside, there is also in real life an envelope function which we saw in just the previous graph. Let us call that envelope function in the spectral domain to be f of omega. So, then this quantity, this sort of typical spectrum lends itself to the definition of a free spectral range for the Etalon or the Fabry-Perot interferometer, or what I have the habit of calling a cavity or an optical cavity or optical resonator. So, all of these I use synonymously, or we use synonymously. So, let us familiarize ourselves with all these terms. So, delta omega free spectral range we can read off from this is on the omega scale, successive peaks are separated by 2 pi divided by t, t being the cavity round trip time, right. So, t is nothing but the velocity of light in the medium divided by the optical path length for a whole round trip. So, that is 2 pi times c divided by L. Now, the FSR can be expressed in terms of wavelength lambda, it can be expressed in terms of wave number 1 over lambda and so on. So, the FSR which is in terms of omega, the angular frequency 2 pi times c by L. In the case of cyclical frequency or frequency, it would have been just c by L, is also just 1 over L when expressed in terms of wave numbers, whereas in the case of wavelengths lambda, there is a lambda square multiplying the 1 over L factor. This is essentially arising out of the Jacobian of the transformation we make between the frequency and the wavelength variables, right. So, a quick reminder of that. But then what we are really sort of interested in this in terms of this the discussion here is to take a step forward and sort of make a leap, which is what we did in yesterday's lecture. So, again please note once again I am hit by the fact that the pi's have become p's and somehow omegas have become w's. Okay, let us live with that once more, it is after all a review of what we did earlier. So, what insight did we gain by analyzing the these functions over here, right. So, let me for the sake of completeness once again write down here that p is pi and w is the same as omega. Okay, so look at the bottom plot, which is omega on the horizontal axis written in terms of 2 pi divided by t, 0 times, 1 times, 2 times, 3 times and so on and so forth. Then as we discussed this yesterday, if we now look at these two plots as two pieces and concentrate only on the bottom one now, what this function, this entire shape consisting of a set of peaks, okay, these are like the teeth of a comb. So, now this can be written down mathematically by convolving the individual line shape or of a given peak, which is essentially sort of similar in across each of these cases. G of omega is convolved with this function for the periodicity, the Shah function or what I was calling the teeth function, written in terms of omega the variable divided by the periodicity of omega at which the peaks occur, which is integer multiples of 2 pi. Okay. So, this is the corresponding function that makes this whole brings about the periodicity in this spectrum, that is multiplied by the envelope which is f of omega over here, right. So, now this mathematical description of E tilde, the complex electric field, written in terms of the frequency. So, it has indeed been Fourier transformed from the time domain to the frequency or angular frequency domain, if you wish, has this functional form. Note that we are not bothering to sort of equate this and make an exact expression come out at this point, that will be a matter of detailed study. We only want to gain a particular and pertinent insight at this matter at this point, and that is got by understanding the mathematical function that describes such a typical resonator transmittance. Okay. So, what did we then do? We said, okay, we understand three important aspects about Fourier transforms pretty well. That is, a convolution in the frequency domain corresponds to a multiplication in the time domain. A multiplication in the frequency domain corresponds to a convolution in the frequency domain. Convolution, of course, here is designated by the asterisk or the star symbol that we have here. Okay. So, now if the spectrum of the electric field that is transmitted from the resonator to outside or from the Fabry-Perot interferometer to outside is this, has this form, it is also clear that these are the sort of this essentially describes the modes that live inside this resonator, right. Therefore, this is the form of the electric field inside the resonator in the spectral domain, right. If I want, I can ask the question, can I inverse Fourier transform this or go from the frequency to the time domain? The general notion being time to frequency is forward Fourier transform. So, now I can do an inverse or a backward process or an inverse Fourier transform going from omega to t, frequency to time, right. So, that can be done if we do that. How do we do that? We do not even want to consider the exact expression. So, we take each of these individual functions, say f of omega, find its Fourier transform, which can be done rather easily. Take g of omega, find its Fourier transform, inverse Fourier transform back to the time domain. Take this Shah function and find its inverse Fourier transform back to the time domain. Okay. All of these are easily done. If I have the individual Fourier transforms of these functions, right, then wherever multiplication occurred, that is f of omega was multiplying this entire convoluted product, okay, of the periodic function and g. So, this would then in the time domain become a convolution between f and whatever else. Okay. Likewise, if we now consider this convolution between the periodic function and g, then this when Fourier transformed essentially becomes a multiplicative product of the individual inverse Fourier transformed functions little g, and we are using of course the same symbol here for the periodic function, but in the time domain. T divided by a periodic, the periodicity essentially turns out to be t, which we know is the round trip time. So, we have then this to be the form of the function in the time domain. It is almost like a mirror image, if you wish, between the two domains in this case. There again are a set of, instead of peaks we have pulses in the time domain, right, and we have an envelope function in the time domain too. All right. So, this is really interesting. However, we must know that the width of an individual pulse, okay, inside the envelope comes from the width of the envelope in the frequency domain. Okay. The whole bandwidth of the of this transmittance function, okay, in the frequency domain is responsible for the width of an individual pulse in the time domain. Okay. Furthermore, in other words, the width of the envelope in the time domain comes from the width of the individual spectral lines or the line shape in the spectral domain. Okay. So, please remember this or like take good note of this. Okay. So, why did we sort of come up to all this? This tells us that if I have a Fabry-Perot interferometer or an optical resonator, that is enough to make light pulses come to light, right. So, we can make a source of light pulses if we have a resonator. That is, a laser can operate in a pulse mode, or we can engineer, not only engineer and generate, we can also control a light pulse, which is typically something that we think about in the time domain by working ourselves and looking at the resonator, designing it or controlling it in the frequency domain. Okay. Furthermore, the point is that when you have an interferometer like this or a resonator like this acting as a source, we typically get a train of pulses. Okay, it is typically not an isolated one little pulse. When you let it run free, of course, you can always sort of do some switching to pick one of these many pulses from the train and so on, which is additional effort, and it is not the natural way in which the resonator would emit pulses. So, the insight that we have is resonator modes plus something else, which is the physical details of the resonator itself, lead us to a pulse train. Okay. That is the take home message from essentially from the previous lecture. So, now today let us jump into the remaining sections that we want to study about the resonator. Now, we will essentially I wrote down the same fact by in terms of a function which describes the pulses and an envelope which we approximated to a decaying exponential, the same physical insight as I was communicating to you a while ago. Okay. So, let us move on with that. Now, we let us just recount for just a moment the free spectral range of the resonator in the wavelength domain. Here I showcase an alternate way to deduce the same free spectral range in the wavelength domain. Although we did this using the Jacobian earlier, now we are doing it through just some finite maths. It is something it is just an instructive exercise to do this. What we essentially wanted to say was that the we have a phase difference. Okay. We take the round trip phase delta. So, going from one peak over here at say 2 pi to the next peak at 2 pi plus 2 pi, which is 4 pi, this round trip phase 2 pi L by lambda between the two successive peaks, okay, which are formed on account of the wavelength moving from lambda to lambda plus the free spectral range in wavelength lambda FSR. This difference should be 2 pi, okay, 2 pi L divided by lambda minus 2 pi L divided by the sum of lambda plus FSR should be 2 pi. So, take this up and do a bit of math, take lambda common out, right, and then we can essentially write the same equation over here by using a bit of Taylor series, Taylor expansion, right. So, take this bottom term and take the first order Taylor term, that becomes a multiplication of 2 pi over lambda times 1 minus here lambda FSR by lambda in the numerator, and then essentially this allows us to cancel off, also take off the 2 pi's at the moment, and we determine the fact that 1 by lambda minus 1 by lambda multiplying 1 minus lambda FSR by lambda is essentially 1 over L, and lambda FSR is lambda square by L. Okay. So, just a little piece of math, another way to determine the FSR in the wavelength domain. What this sort of tells us is that if I made the same plot of the transmittance in the wavelength domain, I would not essentially get equally spaced peaks in wavelength, because lambda FSR depends on lambda square. Okay. So, this is not going to be equally spaced in the wavelength domain. so there's a skewing that's happening between frequency and wavelength, as we would even have expected this ourselves. Okay.